Hello and welcome to ME-2513, which is Mechanical Engineering Computer Applications. The purpose of this first lecturette is to give you an introduction to the concept of numerical methods for a mechanical engineer. For our introduction, we'll use the example offered in the textbook of an object in Freefall. And we'll begin with essentially review material from your Physics 1 course. In Physics 1, one of the things you learned was Newton's second law, and we'll apply that to the object in Freefall. I'll start by drawing a physical schematic to illustrate what's happening. On the left-hand side here, I'll draw a stick figure of my object, in this case a person, in Freefall. I've never been accused of being an artist, so you'll have to forgive me. Basically, there's only one force on the object, and that is the weight of the object, of the person. Weight is equal to mass times gravity, we know. Those are the forces, the cause. The effect is inertia, movement of the object. So I'll redraw my stick figure. And the effect is a mass being accelerated, m times a. It's also good to indicate a coordinate system. So I'll call my vertical direction the y direction, and up is positive. There we go. Okay, my goal now is to turn my physical representation into a mathematical equation. So on the left-hand side, I have the sum of forces in the y direction, and that must balance with what's happening on the kinetic side, which is going to be mass times acceleration in the negative direction, downward. My only force in the y direction is the weight, and that is in the negative direction as well. So I can replace that with minus mass times gravity equals minus mass times acceleration. Now, let's note that we have negatives on both sides and we have mass on both sides. Those can cancel out, and we end up seeing that gravity, the acceleration of gravity, equals the acceleration of the object, the person in this case. In other words, this model is telling us that the person will accelerate with a constant value. Remember, we also know that acceleration is equal to the time rate of change of the velocity. Okay, so this tells us that we have an equation we can integrate to solve for how the velocity changes with time. Let's do that. Let's reorient things here. I will move the derivative with respect to velocity to the left-hand side, and on the right-hand side, I will move gravity multiplied by the derivative of time. Okay, and let's integrate both sides. So the left side integration will be with velocity. The right-hand side integration is with respect to time. Okay, I can carry out that integration, and on the left-hand side, I'll get v minus v naught, or the starting velocity. And on the right-hand side, I'll get the acceleration of gravity times, this will be a simple integral, t minus t start. Now, my initial conditions are my starting velocity and my starting time. In this case, it'd be normal to assume that time starts at 0, and the vertical velocity starts at 0 as well. So I end up with, and I'll try to draw it a little bit more clearly here, v equals g times t. Okay, the velocity of the person in free fall is equal to a constant acceleration of gravity, 9.81 meters per second squared, times the elapsed time. Now there's something wrong here. We know intuitively that the object will not continue to increase its speed forever. We're missing something in the model. Velocity at some point levels off. That's called the terminal velocity. So what's wrong with this picture? Well, our physical model made an assumption that was too limiting. namely the assumption of no air resistance, no drag on the object. So we need to refine this model to make it a more realistic picture of reality. And we'll do just that next. Let's improve our model now by including the drag force of air friction. Now, air friction is a very messy thing in reality. You'll take several courses related to fluid flow in your mechanical engineering curriculum. A pretty good model that's also simple enough for us to use comes from experiment, which shows that the drag force scales with the square of the velocity. Mathematically, I'll say F sub d, so the drag force equals, we'll call CD a constant times the velocity squared, where CD is our coefficient of drag, and that is an empirical constant, meaning it's determined through experiment, curve fitting, for instance, to data, or engineering judgment. Let's incorporate this into our model. So we'll go back to the physical schematic. Here's our free body diagram. And we'll set that equal to our kinetic diagram. We'll also remember our coordinate system, positive y in the vertical up direction. Okay, forces. We still have the weight force, which is equal to mass times gravity. And now we have drag due to air resistance. That will act in the opposite direction of movement. There's our drag force. On the right-hand side, we still have our kinetic effects, inertia, mass times acceleration. Okay, let's see how this changes our mathematical representation. Sum of forces in the y direction must balance with kinetic effects. F equals ma. What are the sum of my forces in the y direction? Now in this case, I have the weight, which is still in the negative direction, but now I have a drag force which is acting in the positive direction. Okay, let's move the mass over to the left-hand side and realize that acceleration is the time rate of change of velocity. If we do that, we end up with, and I'll take the negative over as well, so this becomes now W minus force of drag divided by mass equals the acceleration, which is derivative of velocity with respect to time. Okay, now let's remember that the weight is equal to mass times gravity, and the drag force is equal to a coefficient of drag times velocity squared. Let's insert that into the equation, and we'll end up with, I'll move over here, dv dt equals, so I'll have mass times gravity divided by mass, which just gives me the acceleration of gravity. And then I'll have the coefficient of drag times velocity squared divided by mass. Okay. Well, good luck solving this one by hand. The problem is we've now created a differential equation. Furthermore, it's a second-order differential equation. And furthermore, it's nonlinear, because the dependent variable is multiplied by itself. Okay, we've got a situation where an analytical solution does exist. However, it's pretty difficult to find using our current knowledge of mathematics. This provides a perfect opportunity for us to seek a solution using numerical methods, and that's just what we'll do next. So here we are. And the situation doesn't look too good because we've included just a simple model for drag, and yet we've already ended up with a mathematical equation that we cannot solve by hand. You might be tempted to try to do what we did before and put dv on one side, dt on the other, and integrate. The problem is you cannot get the independent variable, velocity, by itself on one side and the independent variable, time, on the other side. They're intermingled. we can't separate the variables. Okay, so we need to find another method, maybe an approximate method to obtain a solution. And we can do that by looking at the nature of this derivative, dv dt. Okay, let's just create a graph here real quick of time and velocity. We know that the derivative is the slope of the line. So I'll just draw a general straight line segment here. Now that is nonlinear. However, for very, very small segments of time, we can get away with modeling that as a linear or straight line segment. In other words, I can say that dv dt is approximately equal to delta v over delta t. And again, that's good for small values of delta t. Okay, how to use that? Well, I'll rewrite my equation here, replacing the derivative with an algebraic straight line approximation. If I do that, I'll write it in this form. The velocity at one point, which I'll call index I plus 1, minus the velocity at the previous value, I'll call vi. There's my delta v over delta t. So I'll do value ti plus 1 minus t subscript I equals, now my right-hand side, g minus coefficient of drag over mass times the velocity. And I'll pick the first point, vi, index I. Okay? And again, those represent my points. There would be ti plus 1, vi plus 1. My coordinates for each of those two data points. This is my numerical method. What I've done is I've taken a calculus relationship, a differential equation, and I've turned that into something that's now algebra, right? There's no more calculus involved here. I know this is only an approximation, and it's only good for some small value of time. How can I use this with a computer? Well, there's an algorithm buried in this. Here's the algorithm. I'll write this as my new value of velocity equals my old value of velocity plus the right-hand side here times delta t. All I've done is I've solved for vi plus 1. And I have what's called Euler's method. I can start with a known value, known data, a starting velocity at a starting time. And I can move a small delta t, and then I can solve for my new updated value. In other words, the new value equals the old value plus the slope using the old value multiplied by the time step. That is my numerical method, my algorithm that I can now implement on the computer. Okay, let's see how we can implement our numerical method using a computer program. In this case, Microsoft Excel. I've got the Excel file posted on the course website if you'd like to play around with it. Let's see what I do here. First of all, I'll declare some of my constants. I have parameters. Gravity, acceleration is a constant, 9.81 meters per second squared. My drag coefficient is a constant, and I'll use some engineering judgment and set that as 0.25 kilograms per meter. The mass would be of a person. I'll use engineering judgment there and set about 80 kilograms. And then the parameter of time step. Remember, the numerical method is valid for small delta t. How small is small? Well, we can play around with that a little bit later. I'll set it right now to 2 seconds. Okay, I'm going to look at time, acceleration, and velocity. I'll start out with starting time, 0 seconds, and I know my velocity at that starting time, 0 meters per second. With that, I can calculate my acceleration. Remember, the physics gives me the equation for dv dt, or the acceleration, which is, if you look back in your notes, g minus c over m times v squared. So I have cell C1, which is g, minus cell C2, which is the coefficient of drag, divided by cell C3, which is the mass. I anchor those 3 cells because they are always constants up here. And I multiply that by my velocity, which is cell C8 squared. If I do that, because velocity is 0 at time 0, I get 9.81 for my result. Now let's go to the second line. What is my new time? My new time is my old time plus my time step, 2 seconds. I can just drag my acceleration solution down. And what is my new velocity? That's my numerical method. Remember the equation. The new value of velocity equals the old value of velocity, in this case cell C8, plus the old acceleration, or slope, which is dv dt, acceleration, which is cell B8, multiplied by my time step, which is cell C4. My time step stays the same, so I can anchor that cell. At this point, everything else is just drag and drop. And I end up with my solution. You see on the right-hand side, the person starts falling at 0 meters per second, and then after about 10 seconds, they've reached their terminal velocity, which is about 56 meters per second. At this point, the force of the drag balances with the weight of the person, and their acceleration falls to 0. Their velocity is unchanged, in other words. Now let's go back to the time step question. I can change my time step here to 1, and my elapsed time now goes to 18 seconds. I'd have to fill this out further if I wanted to increase the time. The solution appears to be fairly unchanged. Let's go back to 2. Why don't we go up to 3 seconds? Okay, I start to see some abrupt change happen there. Let's go up to 5 seconds. Now this does not look physical, right? I know the person's not going to speed up, slow down, speed up, slow down, speed up, slow down. What I have here is a numerical instability because I'm no longer using a small enough time step to approximate the derivative with a straight line segment. It's the limitation, remember, of the approximate numerical method. So we've walked through all of the steps of a numerical analysis for the mechanical engineering application of dynamics, an object in freefall in this situation. Let's recap what we did. We started with a physical model. That's why you're taking all these varied courses as part of your mechanical engineering curriculum. Those physical models lead to the language of mathematics, which describes the world around us. In this case, even a simple model of an object in freefall with realistic drag led to a differential equation that we could not easily solve by hand. So we seek an approximate solution, a numerical method. Now that numerical method usually involves turning calculus into algebra and results in an algorithm that we have to implement over and over and over again many times, which lends itself well to computer programming. Now for the purpose of this example, we used Microsoft Excel, which is something you guys are already familiar with. The programming language of choice for engineers and scientists these days is MATLAB. We're going to be spending the next several weeks of the course gaining competency in programming structures in MATLAB. Even though we're committing ourselves to MATLAB, the tools you're going to be learning are applicable to any other computer language.